Hello everyone. So today we got a bit of a problem. So apparently there's an explicit formula for the Fibonacci sequence, and it's just a sum of power, and which I thought was really cool. So today we're gonna prove it. So how do we do this? Well, essentially we just have to prove that that this function holds for like an initial value of the Fibonacci sequence, and then that it has the property what is it? The sum of it has the property of being equal to the sum of the two previous terms. So this one, of course. So for this, since we are referring to two previous values, we're going to use strong induction, and we also have to show that it works for two cases. So firstly, we denote F0. We are here using the Fibonacci sequence, which starts at 0. So it's like 0, 1, 1, 2, 3, 5, and so on. So firstly, what is this? Well, if you just input 0 here, you get 1. Okay, that minus the same thing. Okay, so this is just 0. So yes, that works. And we also have to look at the first one, or meaning that it works because it's the same as the actual Fibonacci sequence. And if we input 1, here, okay, we would then, okay, we can extract the 1 over square root of 5. So then we would just have this minus this. And then, of course, the 1's cancel out. It becomes a minus minus. So it's plus 2 square root of 5 over 2. So the 2's cancel out. And then you have square root of 5 over square root of 5. They also cancel out. So then you just get 1. And that is also the same as what the actual Fibonacci sequence is. So now our induction assumption is that our formula for Fn holds for all n less than or equal to k. And then we shall now prove that Fn holds when n is equal to k plus 1. So yes, this is the task at hand. So this is going to take a lot more space, but I'm going to start down here anyway. So essentially what we want to show is that yeah, so I'm just going to input everything according to the... So here our induction assumption doesn't really have, it just assumes this property of the Fibonacci sequence. So essentially this is just what we're supposed to prove with this formula instead. So we are supposed to prove therefore that 1 over the square root of 5 times the 1 plus square root of 5 over 2 to the power of n plus 1 minus 1 over square root of 5 times 1 minus square root of 5 over 2 to the power of n plus 1 is equal to this exact same thing with just n, and then plus also with n minus 1. And also a very, 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 very interesting fact, by the way. Maybe some of you recognize these things in here. And what is this? This is the golden ratio. And this one also, this is, or it's kind of the, this is the real golden ratio, but this is the other golden ratio, you could say. It's basically the solution to the equation, what is it, x squared is equal to x plus 1, I think. Yeah, I think it is. And also the golden ratio, so for you who don't know, is very, very interconnected with the Fibonacci sequence. It is actually the limit as n tends to infinity of Fn over Fn minus 1. So basically just the, well, yeah, the growth rate, you could say, of the Fibonacci, that is a minus. Fn over Fn minus 1. So the new term divided by the previous one. And then you get the golden ratio. So yes, now, so essentially this is what we're supposed to prove. Side tangent done. Okay, so now back to the proof. We're supposed to prove that this is equal to the same thing with just an n, and plus the same thing with an n minus 1 on both, of course. So yes, and now I need to erase some things, so give me one. Hello, I'm back. So I realized now that I may have misspoken before. What we're actually supposed to prove is just that the Fibonacci of k plus 1 is equal to that formula when you input k plus 1. And we are allowed to assume that you can split it up according to how the Fibonacci sequence works. So so we just start with, we have f k plus 1. What is that? That is f k plus f k minus 1. And now, according to our induction assumption, we can exchange these for our formula. So with fk, that is just 1 over square root of 5 times 1 plus square root of 5 over 2, everything to the power of k, minus 1 over the square root of 5 times 1 minus square root of 5 over 2 to the power of k. And then continuing here, so now we have to add that 1 too. So it's just plus 1 over the square root of 5 times 1 plus square root of 5 over 2 to the power of k minus 1 minus 1 square root of 5 times 1 plus, minus 1 minus square root of 5 over 2 to the power of k minus 1. Whew. Okay, so now, firstly, I'm just going to say fuck you to all of these 1 over square root of 5. And just so what yeah, I'm just gonna multiply everything over there and then instead just say that we're actually looking for the square root of 5 times that thing here, right? So yeah, I'm just gonna remove these everywhere, and then obviously we're just looking instead for well, yeah, just this with k plus 1 instead. So so this is of course not a proper equivalent sign, but you understand anyway, I think. Equal to sign, sorry, not an equivalence sign. So now, okay, what do we have here? Okay, these two are the same, and these two are the same, so we can do some factorization. So we can have 1 plus square root of 5 over 2 to the power of k minus 1 times, okay, so there we just add 1, and then plus, sorry, yeah, here we just add 1, and there we add the inside, so just plus the golden ratio 1 plus square root of 5 over 2, and then we do the exact same thing with the other one also, so it's 1 minus square root of 5 over 2 to the power of k minus 1, and then plus, okay, so here we just sorry, it should be a minus sign, minus, so here we just add 1, and then there we add a, well, yeah, the minus golden, so 1 minus square root of 5 over 2. And now, okay, so what we want to get to, where our end point preferably would just be that we get, okay, so we have 1 plus square root of 5 over 2 to the power of k plus 1 minus 1 minus the square root of 5 over 2 to the power of k plus 1. Right? And that is almost what we have here. Okay, so we want here, so as you see, these are the same, obviously, and also these are the same. So if this would be that squared, then we would just be done, right? And fortunately, it is. So here we can just make a quick little note here. So we look at what is that thing squared. So firstly, of course, we add, so we get 3 plus square root of 5 over 2. So we look at, no, sorry, the square root, of course. So therefore, we just look at what is this squared. So we look at what is 1 plus the square root of 5 over 2 squared. That is 1 plus 2 square root of 5 plus 5 over 2. So therefore, the 2's cancel out, this becomes a 6, and then plus a 3. Sorry, over 4. Over 4. Fuck, I'm dumb. Yes, so the 2's cancel out and make a 2 instead, and then you add, and also with the 6. So you get just this thing here inside. I can write it up. So it's just 3 plus square root of 5 over 2. And that is exactly what we have in there. And then we also look at what is that squared with just the minus sign instead. So what is 1 minus square root of 5 over 2 squared? That is just 1 minus 2 square root of 5 plus 5 over 4. And this you can really easily see that this is just 3 minus square root of 5 over 2, which is exactly what we also have here. So therefore, we can just say that this is, that part there is just 1 plus square root of 5 over 2 to the power of k minus 1 times the same thing here, squared minus 1 minus square root of 5 over 2 to the power of k minus 1 times the same thing in here, squared. So therefore the exponents add up and we eventually reach this point. So yes, the video got a bit long, but I hope you followed through and enjoyed the video anyway. So yes, this was the proof for the explicit formula of the Fibonacci, which I found really interesting. So yes, I hope you enjoyed the video, and check out the link in the description, and I'll see you some other time. Bye-bye.